Hello, Chem 30. Let's get into voltaic cells again, talk about half cells, and this is where things are going to start making sense. I know yesterday was confusing. It's all good. Today things come together and you'll see how this works. So today's outcome is that you are going to be able to predict and write the half reaction equations that occur at each electrode in an electrochemical cell. And we're working specifically on voltaic cells today. So first, we have to talk about what a half cell is. It's half of a cell. So when we look at a net reaction, right, a half reaction was half of the reaction. It showed either the oxidation or the reduction taking place. In the same way, when I look at a half cell, it is where either oxidation or reduction happens. It is half of the cell. Now, a half cell will consist of one electrode and an electrolyte. Okay, so I have again electrode. Remember that that is something that is conductive and it's a site of either oxidation or reduction, depending on whether it's an anode or a cathode. Typically it's a solid. And then I have electrolyte, which is a conductive solution, meaning it has aqueous ions to allow anions and cations to move around. A half reaction takes place in a half cell. And two half cells are separated by a porous boundary and an external circuit. You're going to learn about the porous boundary here in just a bit, but what it does is it allows for ions to move through without there being complete mixing of the chemicals in the two half cells. So there's two types of porous boundaries you need to be familiar with. The first one is called a salt bridge. And so what a salt bridge is I have a shape of a U for a tube, a U tube. And then in that U tube, I have an electrolyte. This is often sodium sulfate, much of the time, Na2SO4 aqueous. And then at the ends of this, I have a porous boundary. So they kind of have this labeled as cotton plugs. It could be some kind of ceramic or something that allows ions to move through, but again stops complete mixing of chemicals from happening. So cotton plugs would also work. And so what this is doing is it's separating my two different electrolytes. So this would be one half cell, this would be another half cell. This is missing the rest of the cell, so it's not showing the electrodes or the external circuit, but the salt bridge would connect the two cells for the internal circuit, meaning the movement of ions. The other option, which is a little bit more efficient, is a porous cup. So this porous cup, again, allows ions to move through. It's a material that is somewhat porous, but doesn't allow for complete mixing of chemicals. Okay, so you don't actually have just solutions completely mixing between the two. So when we write out a cell, we use something called often cell notation, which is a short form way of writing out what we have in a cell. And it always goes anode, then I have a vertical line, and then I have the electrolyte that is with the anode. Then I have two vertical lines, and I have the electrolyte with the cathode, and then I have the cathode. So this is always the layout that I have when I'm talking about a cell in cell notation. These single vertical lines are what's called a phase boundary. So what this means is that I have a difference between the phase or the state between the electrode and the electrolyte. So the electrode would be a solid typically, and then my electrolyte would be aqueous. And then I have this, which is my porous boundary. So that is either the salt bridge or the porous cup. So that's my porous boundary. And then I have another phase boundary right here between the electrolyte and then the cathode electrode. So here's a picture of actually a full cell. This is called a Daniell cell, which has zinc and copper together. So I have a zinc half cell with zinc sulfate, and then I have a copper half cell over here. So in this scenario, zinc would be my anode. So I would actually write out, and don't worry right now about, oh, why is zinc the anode? We'll get into that later on. But just trust me, it's the anode. So I'd have zinc, then I'd have zinc sulfate. I'd have two lines representing the porous boundary of my salt bridge, and then I'd have CuSO4 aqueous, and then finally I'd have a single line and copper. Okay, and that single line represents again a phase boundary because copper and copper 2 sulfate are two different phases, copper 2 sulfate being aqueous and copper being a solid. So why is this the way it is? Well, zinc down here is my strongest reducing agent, and then copper 2 is my strongest oxidizing agent. So this is the reduction half reaction, so that will happen at my cathode. So if I go back, this right here is my cathode, because that's where reduction is taking place. So at this, I have copper 2 positive aqueous plus 2 electrons making copper. That is what is happening at the cathode. And then for zinc, it is my strongest reducing agent. So this is where oxidation will happen. So Zn solid reacts to form Zn2 positive aqueous and plus 2 electrons. So this is, as a result, my anode. So this will be the negative terminal of this cell, and this will be the positive terminal of this cell. And we're going to get into building these cells in just a little bit. And in fact, we're going to analyze this cell in a little bit more depth right away here. So here is a nice little diagram of my zinc copper cell. Again, the exact same thing that I just actually had in the last diagram. I'm using sodium sulfate in the salt bridge because I already have the sulfate ion present, and sodium ion doesn't react with anything here, so that works out quite well. So let's take a look at the zinc half cell. As we already mentioned, the reaction that's happening here is the oxidation of zinc, and we know that because zinc is my SRA. So given that it's the strongest reducing agent, it is going to be oxidized, and this is my half reaction. So I have Zn solid reacts to form Zn2 positive aqueous plus 2 electrons. So what is happening here is that this zinc is shrinking over time because the zinc is turning into Zn2 positive aqueous, and it's doing that because it's releasing the 2 electrons. Oh, that was interesting. It was releasing the 2 electrons going up towards the cathode. So that is being lost from the solid zinc. I'm making Zn2 positive aqueous, and then these 2 electrons are going away, just like is seen in this half reaction here. So electrode changes. This is going to be shrinking over time. Again, you guys learned about anorexic ox, which is getting smaller as time goes on. So electrolyte changes, I'm gaining these zinc ions. Okay, and they're actually going to be moving into the salt bridge because my positive cations are going to migrate in the direction of the cathode. Now, what's happening going out of the salt bridge? Well, out of the salt bridge, I actually have sulfate ion leaving the salt bridge and going into the solution in order to balance out the positive charge that's building up here from the loss of the electrons and the Zn2 positive ions being made. So anions are always going to move towards the anode, right? This being the anode. Well, cations are going to be moving towards the cathode. My outer circuit, I have electrons that are moving from anode to cathode, so they're going to be going in this direction. And then for the inner circuit, we already talked about that. Anions will migrate towards the anode, while cations are going to migrate towards the cathode. All right, the half reaction for this, we already talked about this as well, so I'm just going to write it out. It's copper 2 aqueous plus 2 electrons gives me copper solid. So what will actually happen is my copper 2 aqueous that is in this electrolyte is going to come towards and migrate towards the cathode. It's going to meet up with 2 electrons that are coming from the anode, right? Because electrons are going from anode to cathode. And then what will happen is when these meet up, it's going to make solid copper on the outside of this electrode. So I'm going to make Cu solid. So the electrode is going to grow. It's getting plated over time. Fat red cat. The red cat is getting bigger because the reduction, right, red, happening at the cathode, cat. So electrode changes, it grows. Electrolyte changes, I have cations going to the cathode. Once again, so the cations that I have are copper 2 moving towards the cathode. Also, I'm going to have sodium ions leaving the salt bridge, coming out into this solution as well, because I'm losing positive ions as this turns into copper solid. So I need positive ions to come out in order to even out that charge. And then I'm going to have sulfate ions moving from the electrolyte into the salt bridge as well. Okay, so I also have anions moving towards the anode. The outer circuit, we've already talked about this as well. It's moving from anode to cathode for electrons. So that's why I have electrons drawn in this direction, right? Moving from anode to cathode. And then for the inner circuit, we've already discussed that and the migration that's taking place. So that's what's happening in the two half cells. So we've already actually kind of shown most of this, but putting it all together, this is the anode. It is negative, the negative terminal of this voltaic cell. This is the cathode. It is positive. Electrons are moving from anode to cathode. So I draw an electron kind of arrow like that. And then I have cations that are moving towards the cathode. And I have, and I have anions that are moving towards the anode. So anion migration this way and cation migration to the right. Okay, label the following for this cell of cathode, anode, changes to electrons, electron movement, ion movement for this cell. So now we're getting fully into it, going through the motions of everything that's going to be happening for oxidation, reduction, the net, everything else. All right, so let's try this out. I just want to see if I have a half reaction table here. No, I don't handy. Let me pause, grab it, come back. Okay, so here we go. We've got these major entities. Wait for it. So here's my redox table. Let's kind of list what we have in terms of things that we can use. So we've got aluminum, Al solid. We have Al3 positive aqueous. We've got chloride, Cl minus aqueous. And then going to here, we also have nickel 2, nickel, and of course water. Nickel 2 aqueous, chloride we already have, Ni solid, and then we have H2O. Okay, so if we go to our redox table, we see that the strongest oxidizing agent we have is going to be the nickel 2 right here. And then the strongest reducing agent we have is the aluminum. So this is what is going to get oxidized, right? So that's my anode half reaction. And this is what is going to get reduced. So this is my cathode half reaction. So going back to this, my oxidation is Al solid, reacts to form Al3 positive aqueous, and 3 electrons. And my reduction half reaction is the Ni2 positive aqueous plus 2 electrons gives me Ni solid. So this reduction is going to happen at the cathode. And the cathode is going to be the nickel, Ni solid. While the oxidation is going to happen at the anode. And the anode is going to be the aluminum itself, right? So now this cathode, it could be anything. It doesn't have to be nickel. Nickel is just what we're using here, but it could be anything that conducts electricity, and it would actually get covered with nickel. So for example, if we were doing this in class, I could actually take a house key, connect it, and that house key would get plated with nickel. And because the house key is metal, it would actually then react, or not react, sorry, it would conduct, allowing the electrons to get through it for reduction to take place there. Now for the oxidation, that has to be the aluminum because aluminum itself is what is getting oxidized. It's the SRA. So the net reaction, because I have 2 and 3, I've got to do some multiplying here. So I'm going to multiply this by 2. I'm going to multiply this by 3. So I end up with getting 2 Al solid plus 3 Ni2 positive aqueous makes 2 Al3 positive aqueous and 3 Ni solid. I can double check and make sure I'm right by looking at the charge and making sure it balances out. I've got 6 positive for the nickels, 6 positive for the aluminum, so my charge works out. It looks good. Okay, so now let's go back and do like the full analysis of how this would look when I look at my full cell here. Now, I know that aluminum is also the anode by the fact that it's written out this way, right? Anode, electrolyte with anode, electrolyte with cathode, and then cathode. So I'm going to put Al solid right here. I've got nickel right here. So this is my cathode, which means that it is positive. This is my anode, which means it is negative. Electrons are going to travel from anode to cathode, so I can label that right away. This is going to be my aluminum chloride, AlCl3 aqueous, as my electrolyte, and this will be my NiCl2 aqueous. Another thing that I should label, so I've got cathode labeled, got my anode labeled, changes to electrodes, let's label that. Aluminum over time is going to shrink, it's going to get smaller. Well, cathode over time is going to grow, it's going to get larger as I have nickel plating on there. Electron movement, I've got that. Ion movement for this cell. I normally just do this, I just kind of say cations are going towards the cathode and anions are going towards the anode, and I just label it that way. If we want to be really specific, we can do that by actually like drawing arrows for the nickel and stuff, but that gets really tricky to show neatly, especially in this format. Now, if I want to show the half reactions on this diagram, which isn't required from the information here, but I think is a good exercise to show you, what's happening for the reduction is Ni2 positive aqueous is coming to meet up with the 2 electrons to make Ni solid, plating it on there. And then over here, what's happening is I have Al3 positive aqueous being made and 3 electrons leaving, right, as the aluminum Al solid breaks down. I know it doesn't show up very well, but there it is. Okay, so that's a full like breakdown of a cell of what's happening. What I did is I looked here, I realized that this was my SOA, right? My strongest oxidizing agent for the nickel 2. This was my SRA with the aluminum. And then from there, the cell pretty much builds itself. Again, I knew that this was the anode as well based on the format of anode and then cathode. All right. Labeled everything on the cell using the following information. Could try this one out as well. What I would suggest you do actually is first you try it out really quick. See if you can build the cell on your own by making the major entities, analyzing the half reactions, and then you try kind of drawing this, and then come back to this video and see how you do. So what I have is within the porous cup, I have iron, and then I have iron 2 sulfate electrolyte. And then outside of the porous cup and the rest of the beaker, I have silver electrode and silver nitrate solution. So hopefully you've tried it out. Let's take a look and go through what my different entities are and analyze it here. So what I have is I have iron, Fe solid. I have iron 2, Fe2 positive aqueous. I have sulfate ion, SO4 2 minus aqueous. Then I have silver, Ag, solid. I have silver nitrate, so Ag positive aqueous. I have NO3 minus aqueous. Don't know why that happens with my mouse. NO3 minus aqueous, and then I have water as well. I know this is getting messy. So going to my half reaction table here, Oh, and I don't have enough information that it shows silver ion, but silver ion is way up here, Ag positive aqueous somewhere there. So trust me that this is my SOA. It's what I'm dealing with for that. And then iron is going to be my SRA for this reaction. Again, it's downhill because every voltaic cell is going to be spontaneous. So this is my SOA. And then I have iron 2 being my iron being my SRA. So my oxidation is going to be Fe solid, reacts to form Fe2 positive aqueous and 2 electrons. My reduction will be Ag positive aqueous plus an electron makes Ag solid. So in order to combine this to a net, I'm going to need 2 of the silvers. So I end up with Fe solid plus 2 Ag positive aqueous makes Fe2 positive aqueous and 2 Ag solid. Okay, so that is my net reaction. Now, if I'm going to show all my different parts for this, which I should do, so I've got here, this is my iron electrode, Fe solid. And as we talked about, iron is my oxidation, so this is going to be my anode, which means it's negative. And then this is silver, Ag solid. This is where reduction happens, right? Because my silver reaction is my reduction. So this is my cathode. And it's going to be the positive terminal of this cell. When I talk about negative and positive, all this actually means is that electrons come from the negative end of the cell. That's what that is saying. That's why it's negative, and then it flows to the positive end of the cell, right? So just like on a battery, when you see the negative and positive terminal, it's the same. Okay, the negative terminals where electrons are coming from on the battery. Okay, so now I've shown my electrons. So I'm going to have cations moving towards the cathode. I'm going to have anions migrating and moving towards, I actually kind of drew that poorly for the cations. Anions are moving towards the anode. It would be good for me to draw cations instead like this, because it is moving through the porous boundary, which is my internal circuit, is the movement of ions. One thing I didn't mention before is the negative charge loop. You'll notice that electrons are moving like this, yeah, from anode to cathode, and then I have negative particles moving with anions from cathode to anode. So I form this negative loop thing, right, going all the way around. Let's actually get a different color here for my pen to show that. So I've got my negative loop. Oh, that's so ugly. I have regrets. I have regrets in doing that. But this is my negative charge loop going all the way around. Okay, let's just Control Z that sucker and get rid of it. Okay, so now that we've done that, let's talk about a few other things. Break this down. The anode over time is going to be shrinking, getting smaller. And the reason why is that my Fe solid is releasing 2 electrons and making in the process Fe2 positive aqueous, right, which is going in with my iron 2 sulfate. So my Fe2 positive aqueous ions are hanging out here, and my sulfate ions. So those are in the porous boundary. And then for the silver, over time, this is actually going to be growing, getting larger. Okay, I'm going to be getting silver plated on here. And why that happens is because I have Ag positive aqueous that is meeting up with the 1 electron that it takes for this to happen. And then I'm going to end up getting silver solid plated on my cathode. It grows while the anode is going to be shrinking. Now, what's interesting is that for every 1 iron that gets oxidized, I'm going to get 2 silvers that get plated on here when I'm talking about atoms. When I talk about mass, I'd have to actually look at the molar masses to analyze how that would work out. Okay, but it's just kind of interesting, that 2-to-1 ratio when I'm looking at the voltaic cell. All right, so that's that cell. Hopefully that makes some sense. Write out the correct cell notation. Easy peasy, I can do that. I have my anode of Fe solid, porous boundary, phase boundary, my bad. My electrolyte of FeSO4 aqueous as my electrolyte with the anode. Now I got my porous boundary with the porous cap. Now I've got my AgNO3, silver nitrate aqueous, state boundary, Ag solid. I didn't draw the nitrate in here. I probably should have done that. NO3 minus aqueous. All right, good. Moving forward, inert electrodes are something that you should know about. And this is the last thing for today. We can use inert electrodes, especially for the cathode, but sometimes for the anode as well, depending on the half reaction that occurs. Inert electrodes are not involved in the reaction at all. In fact, they're very unreactive materials, but they conduct electricity and they're solids. The most common inert electrodes are graphite, C solid, and that allotrope of carbon does conduct, even though it's a non-metal. Graphite conducts electricity. This is the same as what is in your pencil. Pencil lead is graphite. We also can use platinum or palladium. So PT solid or PD solid. These are more expensive. Okay, so PT, PD, way more expensive than graphite is, but they're very good inert electrodes. Inert electrodes do conduct, okay? But again, they're not involved in the reaction, which is why they are inert. And chemically, these are not very reactive. PT, PD, platinum, and palladium are very noble metals. They don't react, they don't corrode very easily. And then carbon also does not react easily with the stuff we use in voltaic cells. So they are great choices as inert electrodes. When you see things like carbon, platinum, or palladium, they are not going to be the SOA or the SRA. They are just a surface for the reaction, the oxidation or reduction to happen at for the half cell. All right, so that is it for today. That's inert electrodes. Tomorrow we're going to get into half cells and voltages and stuff. Enjoy the rest of your day.